Okay. Welcome, everybody, to this week's episode of the Chalmers Online Functional Programming Seminar. Today's speaker is Philip Wadler from the University of Edinburgh. And the title of the presentation will be Featherweight Go. Before Phil starts, I would like to say a few administrative things. As usual, we deal with questions through Slido. The Slido link is on the YouTube page in the chat. And when you ask a question, please type in your full name, so it is easier for us to deal with. And also, everybody can upvote questions they like. So if you see a question that you like, upvote it so that Phil will see it at the top. Right, there's also a link to the slides that Phil is using, a PDF. So if you want to download that and look at those, that's also recommended. Right, and that's all the administration. So take it away, Phil.
Hi, welcome everybody. It's quite weird doing this, not being able to see people. It really is a brave new world, right? I was invited to do this, so I thought, oh, right, I'll give a talk about our latest work. But that was actually submitted anonymously. You're not supposed to publicize that to the world. Local talks, fine. Talks to the whole world, not so good. And these days, a local talk and a talk to the whole world is the same thing. So if I've outed us to you as a referee for the relevant conference, I apologize. I've already apologized to the conference chair, who said, oh yes, things like that can happen these days. All right, you're forgiven. But I'm very sorry that I did that. It's part of the brave new world that we're in. I should begin with a joke, but there's no point in telling a joke because I can't see or hear any of you. That was a joke. If that was funny, I have no idea. You could put smileys in the chat window, but I'm not allowed to look at the chat window because it's 20 seconds delayed from my talk. So please do put a smiley there. I'll be able to tell later if I was funny or not. So this is joint work with many people. Robert Griesemer at Google, Raymond Hu at Hertfordshire, Kokke at Edinburgh, Juliet Lange at Kent, Ian Lance Taylor, also at Google, Bernardo Toninho at Nova, me, and Nobuko Yoshida. I've tried to put in pictures for all of us. I think Nobuko sent me the best picture. Let's see. And as Kun mentioned, you can put questions into the Slido as we go along. There are two kinds of questions that people have often. One kind of question is for clarification, and another kind of question is for discussion, right? Tell me more about this bit. People have both kinds of questions during the talk. Please save the discussion questions for at the end. But one of the huge advantages of a live talk is that if I say something that you don't understand, you can live ask for clarification. And Kun has kindly volunteered to keep a look at the Slido, and if there are clarification questions I'm missing, to notify me about them. So please feel free to ask those. It's important to ask those. Go ahead and write clarification at the beginning if you want to make clear that that's a question for now, not a question for later. And I hope we'll get some of those. Are there any questions yet? Oh, I have to wait 20 seconds after saying that. I'll just press on for a bit, but I'll ask that again in a moment. Now, the other thing that I wanted to say, it doesn't like my keyboard. If I came to a technical talk and somebody starts spouting politics at me, I would not be best pleased. On the other hand, right now, we're at a very unusual moment in the world. This is the Black Lives Matter demonstration in Hollywood Park in Edinburgh yesterday. We're supposed to be under lockdown with social distancing, but people still felt this was so important that a very large number showed up. I think this is more than I saw at the last independence rally for Scotland. So this is clearly something that's of the moment. And I think to ignore it would be to say, well, we as scientists don't give this any importance whatsoever, and I don't want to do that. So I'm just going to very briefly point out a couple of things. Here's a resource I found online, something called Campaign Zero. You can see they have various constructive recommendations for ways to take things forward. Their URL is joincampaignzero.org. You can have a look at that and look at those if you feel like it. There are many, many other resources. I encourage you to follow up on whatever resources you think is appropriate for you. As scientists, there is actually something that we do about prejudice. It's called double-blind refereeing. And it's a very important part of moving science forward, right? All the different things that we do to encourage objectivity are very important to science. And this is one, and it can actually work against prejudice. I have to admit that up to now, I've thought of double-blind as mainly important for avoiding things like gender prejudice. It's sadly much less important for race prejudice because we have very few people of other races who do functional programming, who work in our community. And that's something that I think we need to work to change. But double-blind can help for this. Now, the thing is, in our community, in programming languages, many of the major conferences don't use double-blind. They use something called lightweight double-blind. So lightweight double-blind is blinded for the initial review, but then it's unblinded before the people who've made the review decide whether to accept the paper or not. And one thing that we understand about prejudice of all kinds is that it's not always conscious. Indeed, I've seen people commenting, you know, if you say you're not racist because you never consciously do anything racist, well, that's not the issue. People doing things that are consciously racist. It's all the systematic, built-in, and unconscious things that happen. So I am worried that even when we use lightweight double-blind, people might subconsciously, not aware of it, have various forms of prejudice that affect their decision. So I'd like to encourage our community to move away from lightweight double-blind and to double-blind. I'll be doing what I can to lobby for that. I know other people have other views, but I think that moving from lightweight double-blind to double-blind is one way we can deal with this. I explained about lightweight double-blind to my son once, and he came up with what I think is the appropriate name for lightweight double-blind. He said, oh, that's not double-blind. So I think that's what we should call it from now on. And maybe we can move to true double-blind. Okay, so that's all I'm going to do about politics. And now I'm going to move on to talking about programming languages. And I'll just pause here to see if there are any questions. And while we're paused, I'm going to try an experiment. I am going to go into, there it is. I'm going to stop sharing. Right, does this mean you can all see me now big? Because I hate watching all these other things. The person just always in the corner, and that's no fun at all. So I thought I should try to appear big every now and then. Am I appearing big? I don't know. No feedback. Somebody put something in the chat. Kuhn, put something from Kuhn to everybody saying, can you see me big now or not? And in 20 seconds, I'll find out if this worked or not. Okay, I'm going to go on with the talk, but
you are big, Phil.
Fantastic. Okay, so I'll do that. Just want to pause for questions every now and then so that people can actually see the lecture rather than just seeing slides, because I found just seeing the slides and not seeing the lecture to, I just wanted to see the lecture every now and then. Maybe you guys don't want to see me tough. You're going to see me anyway. Sorry about that. So let's go back to share screen. Okay, let's move on. Right, so the beginning of this is there's this programming language called Go. I knew absolutely nothing about it, except that it's very widely used by some people. And I knew that it didn't have parametric polymorphism as part of the language. And I get a letter from Rob Pike, who I know. We used to work together at Bell Labs. And he wrote to me and said, would you be interested in helping us get polymorphism right and or figuring out what right means for some future versions of Go. And this is at a time when they'd begun to circulate some proposals for what polymorphism might look like. So how often does one get a chance as a programming language theorist to have impact on a real language that's widely used? So this is a fantastic opportunity. And of course I said yes. And you saw that long list of co-authors. So that's a couple of people who are on the Go team at Google. That's Robert and Ian. And a bunch of other people who are colleagues of mine from the ABCD project, which is involved with session types, but a lot of their session type work was with session typed Go. So they knew Go. So I teamed up with them and we tried to make some progress. And one thing that I've been involved with in the past is Featherweight Java. So this was at the time that we came out with this, lots of people had been doing formal models of Java. And the goal was do a formal model that is as complete as possible. And Benjamin and I and Atsushi got together and said, let's do a formal model of Java that is as incomplete as possible, as simple as possible. So it's a very tiny language. It just had 5 expression forms. And indeed, the first use of it was to both do a model of Java that was very simple, and to then extend that to support generic Java, which for legal reasons was called GJ, which indeed became the basics of generics in Java, which were added a few years later. So I said I wasn't going to talk about politics, but there was actually a lot of politics in that. But I won't go into that. But we published this paper, and it turns out doing a model that is as simple as possible is a great idea. So there's several papers on models that are as complete as possible. The most popular of those has just over 500 citations. And our paper on Featherweight Java, the journal version of it in Topless, has just under twice that. It has just over 1,000 citations. So there is something to be said for being very, very simple, maybe even too simple. So I hadn't actually thought about this, right? But this is exactly what we want to be doing for Go. And one of my colleagues pointed this out to me. I said, oh yeah, that's a really good idea. So that's what we set out to do, is to make a model of Go rather than Java that's as simple as possible, and then to look at how that would change if you added generics. So, right, I just said we did this for Java. Is there any point in doing it for Go? Is there anything really different about Go that's interesting as compared to Java? And the answer is yes, there is. So Java is based on classes and interfaces, and for Featherweight Java, we even took out the interfaces. We just had classes. Go is based on structs and interfaces. I'll give you an example in a minute so you can see what that's like. But because of the way that works, you can't get rid of interfaces. They've got to be in the simplest version. So there's some difference going on there. Java, as most object-oriented languages, uses nominal subtyping, whereas Go uses structural subtyping. So basically, in Java, a class is a subclass of another superclass if it says it is. In Go, a struct implements an interface if it has the methods required by that interface. Here, the only way that a class can be a subclass of a superclass is if you declare it specifically to be so. So in particular, that means that if you've got a class C and you want D to be a subclass of it, D must be declared after C because D must refer to C. And when you declare D, you must say D has C as a superclass. But for Go, it doesn't work that way. You declare structs anytime you want. You declare interfaces anytime you want. You declare functions on those structs anytime you want, or methods, they're called. The keyword is func, but the name for it is a method. You declare methods on those structs any place you want, And if there are enough methods on the struct so that it implements all the methods required by the interface, then the struct implements the interface. So Java is a closed world, but Go is an open world. You don't actually know, when you're just looking at struct, which interfaces it might belong to. It might belong to interfaces that haven't been declared yet. And by the way, in case you just think that's a Java Go thing, if you look at Haskell, right? In Haskell, we've got data types and type classes. So type classes are not like object-oriented classes, except they have a similar name. And we've got more or less structural subtyping, but just like in Java, we've got a closed set of supertypes. A type class only has another type class as its supertype if it is explicitly declared. So in that sense, we are not structural, we are nominal. And that actually is a limitation. So for example, if you look at the history, the monad type class was around for a long time before the functor type class came in. But it's very convenient to have functor be a superclass of monad. So at that point, in order to do that, monad had to be redeclared. You basically had to just update everything throughout the whole library. So everything had to be recompiled against the new library where functor is a superclass of monad. And it's been clear to me for a long time, it would be nice to be open. It would be nice to be if you could declare monad and later declare functor and automatically have functor as a superclass of monad just because of the relationship of the functions in each type class. So that is what Go has built into it. And that's actually a very nice feature. It would be nice if in future we could retrofit that to Haskell, possibly using Go as a model. But there is something in Go that's important and useful and which you don't have in Haskell.
Phil, there's a clarification question.
Yeah.
On the Slido.
Okay, let me just pull up the Slido. It says Slido to me. Ah, there's the question. What is monomorphization? Thank you for that question. That's the next thing I'm going to explain. So the last point here is about erasure versus monomorphization. In Java, the way that generic types or polymorphic types, there are two different names for the same thing, are implemented is by translating back to Java before you had generics. So you translate Java with generics to Java without generics. And the way you do that is just by erasing all the type parameters and replacing them with the object, which is the bound on those type parameters. And that has some advantages, but it's very simple. It avoids the exponential blow up that you get with things like templates in C++, but has disadvantages. If you want to create a new array at a type variable, you can't do it. If you want to cast to a type variable, you can't do it because that's not supported by Erasure. So it's a very simple way of implementing things, but it leaves out some things that you'd like to do. So the Go team had already decided that they wanted to implement generics, again, by translating Go with generics to Go without generics, but the translation they were looking at is monomorphization. So I'll give you a detailed example of that later, but basically it means if I've got a generic type list of A, and somewhere I form a list of bool, and somewhere I form a list of int, it turns out those are the only two kinds of lists that I have in my program, then what you get is a final program that is in Go without generics and has list bool and list int as two distinct types, but on which you can do all the appropriate things. So you compile a program by expanding it out. Now, just like with C++, this can lead to a huge amount of blow up. But also, just like with C++, it gives you efficient codes that's just as efficient and just as powerful as if you hadn't used generics. So, excuse me. So this is the first implementation method that we're looking at. It might be good to look at other implementation methods, such as combining some form of monomorphization with some form of passing runtime type information. And we've looked at that a bit, and we intend to look at that more in the future. But as a start, the first thing we're looking at is monomorphization. I hope that answered your question. You can ask a further question if it did not. And I will just pause for a moment. Again, going back to Zoom. And, oh, I can't even see the Zoom window, so I can't see myself, but that's all right. Okay, everything okay? Kun, is everything okay?
Yes, there's some more questions that you could take now, or you can take them later.
I'll go back to those questions later. Those aren't really clarification questions. I hope people will raise them at the end. Okay, so let me go on. So let me do a bunch of examples for you. So first we'll do one example in Featherweight Go, and then all our other examples will be in generic Go. And then after enough examples that you can see what's going on, I will, if there's time, show you a bit about monomorphization, show you a bit about how we formalize this. So here's some code in Go, which is also code in Featherweight Go. So type any is an interface. It has no methods in it whatsoever. So remember what I told you? A struct implements an interface if it defines all the methods required by the interface. So from this, you can see that every struct you declare will implement the any interface. Similarly, one interface implements another interface if the first interface defines all the methods that are required by the second interface. So that's if the second is a subtype, if you consider it as a set of methods of the first. So again, you can see that empty is a subtype of everything. So every interface implements this interface. And now we're going to find a function interface. So what's a function? It's something you can apply to an argument. So apply takes an argument, which we'll call x of type any, and it returns an any. And the technical name for this is a method signature. So it's got the method name, apply, followed by the method signature, which in this case says it takes one argument of type any and returns a result of type any. And then I said, you can declare structs. So how do we do this? Sorry, you can declare structs, and then structs can declare methods. So here's an example. I've got a struct called incr, short for increment. It has one field called n, which is an integer. By the way, here I've written int in boldface, because in Go, int is a primitive. And for the examples, it's easiest to show int as a primitive. But in Featherweight Go, we have no primitives. All we have are structs and interfaces. Once I've explained structs and interfaces, if you think about it for a bit, you'll realize, oh yeah, that's actually powerful enough that I could implement Booleans, I could implement conditionals, I could implement natural numbers, I could implement, using piano arithmetic today, sums over natural numbers. So you could mimic everything you need just in Featherweight Go. But for presenting the examples, I'm going to assume we've got primitives. So we've got n, which is an int. And then we've got a method, func, which has a receiver whose type is increment. And you can give this any name you want, but because receivers are often called this, I've given it the name this. I could have called it Fred instead. And here where I wrote this dot n, I could have just written Fred.n. And then apply takes x, right, an argument of type any and returns an any. What's it going to do? it's going to return x. Now, x has type any, but we want an int. So we do what's called a type assertion, which is just like a cast in Java, except I think it has much better syntax because you write it after the thing rather than before the thing. So x dot int, cast x to an int if the anything happens to be an int. And if not, the technical term is it panics, which just means that it raises an exception. But in the correct case, it returns an integer, and then we can add that to this dot n, which is an integer. So we just do integer addition here. We return an integer, and integers implement any. So this is okay. You could always return a value that implements the result type you're supposed to have. You can always pass as an argument something that implements the type you're supposed to have. So we could pass an int in to apply directly. But apply must be declared with exactly this signature, any and anti. We cannot declare it with, say, int and int, which is kind of what you'd like here. But we're not allowed to do that because a key feature of Go, something that keeps it very simple, is when you've got an interface like this, something implements the interface if the method name is the same and the method signature is identical. So it doesn't care what names you use for the arguments, but this name must exactly match the declaration. This must exactly match the declaration.
Phil?
Exactly.
There's a clarification question about types and interfaces.
I'm sorry, just repeat that.
There's a clarification question about types and interfaces.
Right. Is interface coterminous with types? Nope, there are two kinds of types. You can have a type which is an interface, or you can have a type which is a struct. Okay, and those are the only two kinds of types that you've got in Featherweight Go. You could also have a type which is a primitive type. We'll see an example of that later in Go, but we don't have that in Featherweight Go.
There's another question, a clarification question.
Which is?
At the top.
How will erasure be slower than monomorphization? Because of more things to do at runtime. Right, if you monomorphize, and you've monomorphized a primitive type like int, and you write x plus y, where it's known that x and y's are int, then you can just implement that directly with your op call to addition, whereas otherwise you have to do an indirect call through a v table or something. So monomorphization makes operations on primitives much faster than if you do things via erasure. Okay, let me go on. So here's one example. So this is the increment function. So incr of n is the function that adds n to stuff. Similarly, pause, again, it goes any to any, but this time, pause is a struct with no fields whatsoever. And what the thing on this receiver does, if something is known to have type pause and we do an apply to it, is it's going to take this argument, convert it to an integer again, check whether that's greater than 0, and return that Boolean, which again implements any. So it can be returned as an any. So this always takes an int, returns an int, and panics otherwise. This takes an int and returns a bool. And if you give it anything other than an int, it will panic. And then as a more complicated thing, we can do compose. So compose has two fields, both of which are functions. And then here's our method. So it takes one argument, which is this struct, and apply. And again, it takes an argument, which is an any. It returns an any. What are we going to do? Extract the f field from that structure, apply it to x, and then extract the g field from the same structure and apply that to the result. So it applies f and then applies g. So it's the composition f followed by g, which in category theory, we often write as f semicolon g or g circle f. So that's obviously apply. And notice everything matches up neatly. They're all any's. So anything's fine. Everything's fine. We don't need any type assertions here. And as an example, h could be the function where we compose the increment by -5 function with the pause function. And then if we apply that to 3, this will first increment 3 by -5, so that's -2, and check whether -2 is positive. It is not, so this returns false, but it's false of type any. So if we want to assign it to a Boolean, we will then have to do a type assertion that's a Boolean. It would panic if this wasn't a Boolean, but in this case it is. So B gets assigned false. Okay, so I'll just pause there for a moment. Any other clarification questions? I just noticed there's a sort of clarification question from Simon saying, is monomorphization inherently a whole program transformation? I think so. That is a significant cost. Yes, Simon, you are right. It is a significant cost. And yes, it's whole program, which for many purposes you might not want, but that's what we're looking at in the first instance. So good clarification. Thank you. Right, shall we? Oh, see, there's another good question from Simon. He says, is Haskell static monomorph in pause? In Haskell, static monomorphization is impossible because of polymorphic recursion. Oops, it's moving. So can we do this for Haskell at all? Well, you can do it for the subset of Haskell without polymorphic recursion, but you're absolutely right. When you have polymorphic recursion, you cannot have monomorphization. So we're going to rule polymorphic recursion out for generic Go when we want to monomorphize it. Okay, let me go on. Oh, I see what I should stop sharing. All right, doesn't matter. Let me go on. Functions in Featherweight generic Go. So let me show you the same thing now using generics. So any is just as before. Function now, as you'd expect, takes 2 type parameters, A and B. A is the type of the argument, B is the type of the result. And in generic Go, just like in generic Java, whenever you have a type variable, you give a bound on that type variable. So this says you can have any type you want as long as it implements any. Ha-ha! Every type implements any. So these can be any type you want. And these types, by the way, can range over either interface types or struct types, any interface or struct that implements any, which in this case is every type whatsoever. And so then the only method there is apply. So now incur is going to be just as before, and apply, aha, now we can say apply takes an int and gives you an int, and this will implement exactly the interface, going back here, function int. So for function, we instantiate A to int and B to int. The method should have the signature apply with an argument of type int and a result of type int. So now we don't need to do any type assertions, and we take an int and we return an int, as you might hope. And so we don't need a type assertion here. We can just do x plus this of n. Here again, we take an int to a bool, so we just do x greater than 0. And compose, now we take 3 types, A, B, and C, each of which is bounded by any. And then f is a function from A to B, G is a function from B to C. This definition is just as before, and everything lines up just the way we hope it would. So this is an A, this returns a B, this takes a B, it returns a C, and we're supposed to return a C. So everything lines up neatly. And then when we actually use the things, let H be a function from int to bool, which we're going to get by composing, and write those 3 types A, B, and C are going to be int to int. So we take an int to int function and then an int to bool function. and incr minus 5 is our int-to-int function, pause is our int-to-bool function, and now we can say h apply 3 and assign it to a bool, but no type assertion is required.
Phil?
Yep.
There's a lot of
You can
clarification
see
questions.
me, I hope. Oh, did that? Yeah, I guess it stopped sharing. Okay. Sorry.
There are 3 clarification questions.
Okay, I see one. Do we need downcast generics? E.g., let bool equal something dot bool. Right, but the dot bool, the bool needs to be in parentheses. That's the syntax for a type assertion, but that's exactly what you need to do. And I saw an example of that. What's the problem with omitting the last dot bool and inferring? So I'll say a little bit about type inference, but I don't think you'd want to do type inference here. A place at which you might panic is a place that you would like indicated in the source code. So the problem with inferring here is that you couldn't tell which places could panic and which can't. And when we designed generic Java, we were very careful that those places that could, the word isn't panic in Java, it's a runtime exception for a cast exception, I think it's called. You explicitly have indicate in the code wherever those can occur. And that's the only clarification question I see. Are there any others? Oh, here's one. What's the difference between interface types and struct types, given that struct types appear to be usable as interfaces? No, you cannot use a struct type as an interface. A struct type will have methods on it, and those methods will implement an interface. But a struct type is not an interface. An interface is implemented by any type that has the same methods as declared in the interface. A struct is only implemented by the same struct. Okay.
There's one more.
What's polymorphic recursion? The clarification answer to that is advanced. If you don't know, I'm not going to explain it during this talk, so I can press on, but that's easy for you to look up. It is important, as Simon explained, for whether you can monomorphize or not. Okay, another example, list and map. This time I'll just do them generically. Oh wait, I need to share my screen. How do I share my screen again? Here's how I share my screen again. Okay, Kun, can you see my screen again?
Yep, everything okay.
Okay. Yes, this is all much more fiddly than I'm used to, so apologies if I'm not very smooth with doing it. Right, so let's look at how you would define list and map. So list is going to be an interface. It's parameterized on the type of the list elements. Again, these are bounded by any. And map, now we get another interesting feature, which is a method, as well as taking a value parameter, like f is a function from a to b, may take a type parameter. So this might be list of int, a might be int, b might be bool. And then we're mapping a list of ints to a list of bool. So I hope that's clear to everybody. And then nil of any type A is a struct with no things, and cons of any type A is a struct with 2 fields, a head of type A and a tail of type list of A. Notice we haven't explicitly said here that a list is either a nil or a cons. A list is anything that implements map. And the only thing we'll be able to do with lists is map over them, which is not very interesting. So you might well want to have more methods in here. I'm just doing a very simple toy example, but you might want append here, you might want filter, what have you. You might want head and tail, or you might want a version of head and tail that is type safe in some way. So you might want case expressions in some form, which would then take the nil branch and the cons branch themselves as functions passed into the case expression. So we can do all those things, but I'll just look at map. And we just got 2 ways of building a list. nil and cons. Notice this has to be a list, right? Because it can't just be a cons again, because then we would get an infinite list, which would be very hard to fit into memory. In fact, structs are implemented very efficiently. They're completely flat. Interfaces are implemented as a pair of things, a struct and a dictionary that points to all the methods you can invoke on that struct. So in this case, this would be, say, cons and a pointer to a dictionary that gives us map. And then somebody might have a clarification question. Wait a minute. Why do I need to pass A into nil? Why do I need to know that that's an empty list of integers as opposed to an empty list of bools? That seems silly, but it's actually required here, and you'll see why when we try to declare map. So, right, we've got map over nil and map over cons, map of an empty list of A's. What's it going to return? Well, what's the signature? It's map. It takes B, which is the result type. It takes F, which is a function from A to B. It's going to return a list of B, and it will return an empty list of B's. Why did we need A here? Because we need to declare the type of F, which is a function from A to B. If nil didn't have this A in it, we couldn't give the type of the function, and it wouldn't match exactly, and we'd be in trouble. So we actually have to distinguish empty list of ints from empty lists of bools.
Phil?
Yeah.
There are two clarification questions.
Yeah. Why name the arguments in interfaces just for readability? The names are ignored. And I don't see another clarification. Ah, there it is. So neither a nil nor cons needs to be a list. Well, I could declare nil and cons and not declare map on them, and then they wouldn't be a list. But anything that implements map with this signature will be a list. It's really a shame I can't see people nod when if they understand this.
There's one more question.
The declaration of nil did not mention list at all. How come? Remember what I said, right? It's an open typing system. It's not nominal. A structure implements an interface if the structure defines all the methods required by that interface. So if we go back, we see that the list interface has just one method on it, map. And nil defines map with the correct signature. So nil implements list. And similarly for cons. So let's go on and look at cons. So now we've got a receiver. Notice that this time I'm calling the receiver X's. I called it this before. I can call it anything I want. So now I'm calling it X's. So X's is a cons over A, which is bounded by any. And then map takes a B, which is bounded by any, and a function from A to B, and returns a list of B. And how is this defined? We do a cons of B, where the first field, so this is called a structured literal, and it's just the structure name followed by each of the values of the structure field. So its head is what you get by taking F and applying it to the head of X's, and its tail is what you get by taking X's, taking its tail, and then mapping at type B F over it, which is of course exactly what you'd expect for map defined at cons. And then, for instance, we can let X's be a list of int. So that'd be cons int of 3 and cons int of 6 and nil of int. This is just the list 3, 6. Notice it's Featherweight Go requires us to supply all the parameters. So we need to say cons int here. We need to say cons int here. We need to say nil int here. And here, when I applied map, I needed to say map B. All of those you might want to infer. And again, in this case, you could infer them safely. It wouldn't be that you're hiding a possibility for panic. So it's quite reasonable to infer these. We've not looked at doing that inference for Featherweight Go but that's very important for future work. You want to be able to infer that stuff. Okay, so X's is the length 3, 6. Y's is also a list of int, which we get by mapping at type int increment over it. So increment must be an int to int function. And indeed, if we do increment -5 over this list, we get -2 for the first element and 1 for the second. And I've dropped the ints here just so that it fits on one line. But again, as I said, we're not doing inference right now. And then Z's can be a list of bools, which we get by taking Y's and mapping at bool over at pause. And so that gives us false, the list cons false, cons true, nil. Again, if you did this without generics, to assign this to a list, actually, lists would be okay, right? We wouldn't need to do any type assertions because it would be a list of any, but we'd have no guarantee about what kind of elements appeared in the list. And there are all sorts of places where you need to extract an integer from the list, where you need type assertions, which we do not need here.
Phil?
Yep.
There's one more clarification question.
Are method names global, or can we have map in multiple inferences? So they are global, and the global rule is, it's something simpler than overloading. From the receiver type and the method name, that must specify a unique method body. So for each receiver type, you can only declare the method name once. But at different types, you can reuse the same name. So that's very important. So capital S string with no arguments is a method in Go that's quite standard, and you use that to convert an arbitrary data structure to print it out as a string. It's like show in Haskell. Just like interfaces in Go are like type classes in Haskell. And sorry for the pause. Oh dear, I've lost track. Where was I? See, if I had an audience, somebody could remind me. But there's nobody in the room with me. I'm all on my own, and it will come back to me in a minute. What was the question about? Hold on, let me pull up Slido again, that will remind me. All right, our method name's global. So you can have the string method on many different structs because just the name of the receiver and the name of the string method has to specify what its body is. So you can have string on any different struct you want because that's a different receiver type. So you get this very simplified form of overloading. You never get overloading with regard to the argument types, but you do get overloading with regard to the method names. Okay, let me go on and give another example where we have a bound other than any, and this is quite an interesting bound. So eq is just like the eq type class in Haskell, except it's going to take a parameter. And that parameter is going to be an A that itself implements eq of A. So this is how we guarantee that when you have an integer, that it's equal to an integer, and a bool, that it's equal to a bool. So let's see how that plays out. So the eq interface has one method in it, equal. So it'll have a receiver, of course, and its receiver's type, in fact, will be A, which is enforced by this. But its result type will also, its result type will be bool, but also takes an argument. So there's a receiver and a single argument, in this case called that, which is also of type A. So an example, let's define the type big I int, which is just going to be the same as primitive built-in int. We cannot define methods on built-in int, but we can on big I int. So here we have a func which has a receiver of type int, which is equal to something else of type int and returns a bool. And what do? We check that this is equal to that. Similarly, for bools, we can then define equal, which takes a bool as its receiver and a bool as its argument and gives us this is equal to that. And this works. Remember that the argument here must exactly match the signature, but it does because this is a type parameter. And in this case, int implements eq of int in fact, by this very line. So that's allowed. And here bool implements equal bool, again, by this very line. So that's allowed. So this is what's called F-bounded polymorphism, which is a horrible name, but it's a very nice concept. It was first introduced for variants of system F, although the F there stands not for system F, but just for this thing here, sort of a function of this argument. So in that way, it's function bounded, which is abbreviated to F-bounded. So we've got F-bounded polymorphism here. This is exactly the same thing is already done in generic Java. So this is something that it's a bit complicated, but we know that people can cope with it if they need to. And you might want syntactic sugar that makes that nicer. The Go team is wondering about that. But again, Featherweight Go and Featherweight Generic Go are supposed to be as simple as possible. So we just require all this written out in full. And then here's a more interesting example. So now we've got pair. And a pair has a first component of type A and a second of type B. A and B can be bounded by any. And then we want to define equality on pairs. And we've got a choice here. We could do a type assertion at runtime, so dynamically check that this is something that belongs to the correct eq interface. But it's much nicer to be able to say this statically. So now we're going to say this pair here is over a type A such that A implements eq of A and such that B implements eq of B. That's exactly the kind of pairs on which you want to define equality, because what's the body? We'll extract the first component and see if it's equal to the first component of the other argument. Extract the second component of the receiver, see if it's equal to the second component of the argument. So this is all statically well typed, but this has violated what is a principle of Go up to now, which is the receivers must have exactly the same type. So when there are no type parameters, that's appropriate. But here we're generalizing that to say, no, it doesn't have to have exactly the same type as long as this interface here, which is a bound, is below this interface here, which is a bound, it's okay. And that gives you a lot more power, as I will show in my final example. So this is a proposal we've made to the Go team, and they're considering whether to accept it. But they can see that this would be very useful, right? Otherwise, the other choice, if you want to have pairs which were statically okay for equality, is you get type pollution and you say, okay, A and B, A here will be bounded by eq of A and B by eq of B. So now we can't have pairs over any type, but only pairs over types that support equality if we want to have equality on pairs. So we can avoid that restrictiveness by allowing this generalization where the bounds here can be subtypes of the bound here. Okay, so that's all I wanted to say about that. I'll just pause for a moment again, but I think I'm not going to stop sharing because it's too fiddly. But are there any other questions at this point?
There are no clarification questions, but I just wonder how long you plan to go on for, because we can
This
go.
This is my last example, so I'm going to finish up in 7 minutes.
Okay, good.
Okay, so here's something that's of great interest to me and to other people. Is called the expression problem. I gave it the name, the expression problem. In a little note I wrote, we were considering, could we do this in Java? And the answer, I thought, here, we can do it if we make this funny change. The funny change never got made. So you can't do it in Java. Scala now has some things that does support doing it. But the goal is to define a data type by cases, where one can add new cases for the data type and new functions over the data type without recompiling existing code and while retaining static type safety. So remember that Go, you define structs and you define methods, funcs, over those structs separately, and you define interfaces separately. All of those can be in separate piles. I'm not actually sure how Go compiles. I'm not certain if that's all separate compilation, but those are all separate files, which is very close to separate compilation. So Go looks like a good model, possibly, for dealing with this. And with the generalization I showed you on the previous slide, we can do this. So the idea is, in a functional language, rows are fixed. Those are cases in one can think of cases as rows and functions as columns in a table. So in a functional language, the rows are given. You don't change them. You've got one data type declaration. It tells you what all your cases are. But in other files, you can then easily add new columns, new functions over that data type. In an object-oriented language, it's the other way around. The columns are fixed. Those are your methods in a class declaration. You declare that class in a single file. You can't add new methods later. But rows, new constructors, are basically subclasses, and you can define those in new files. So you can add new rows later. The question is, can we make it easy to add both rows and columns rather than picking functional languages which make columns easy to add or object-oriented languages which make rows easy to add? Can we make both easy to add? So here's our little matrix. So what I'm going to do is show you the simplest possible example of this. I only made two contributions to this. One was to call it the expression problem. The other was to come up with a very, very simple example. The previous examples sort of went on for pages, and mine is less than half a page. And the idea is we've got an expression type with just two constructors, num, which is a numeric literal, and plus, which takes two expressions as arguments. And then there are two things we want to do with these. One is to eval them, and the other is to print them. So this would be show in Haskell, converted to a string. And I'll define these in the order 1, 2, 3, 4. But the whole point is we could do these in any order, right? Instead of doing first this column and then this column over this fixed data type, we could first define num and eval and string over it, and later define plus and eval and string over that. So we might, for instance, do it in this order instead. So the order is not fixed here. So eval on num, we'll define an interface, evaler, which has an eval method, which takes a receiver and converts it to an int. And then we have a num struct, which just has a value in it, which is an int. And if our receiver is a num, and we do eval on it to get an int, what do? We return the value in the e struct. Very straightforward. How about eval on plus? Now, right, the two subfields of plus should be expressions, but we don't know all the things we can do on expressions yet. Maybe we can do more stuff than just eval. So plus takes type any for its field. But for defining eval over plus, we're going to put a bound. It's not a of type any, it's a bounded by evaler. So the fields of the plus must be things we can eval, and then we can eval the plus. And how do we do that? We take the left component, eval it, we take the right component and eval it, and then we add the two together. Okay, so that's eval. What about strings? We've already defined num. Now we define a new interface, stringer. So stringer has in it just one method, string, which takes no arguments and returns a string. And what does string over a num do? It takes the value of that num, converts it to a string of digits, and returns that string of digits. So sprintf %d just means convert that integer to a corresponding string. And then what do we do for plus? Again, now the fields of plus must be things which satisfy the interface stringer, and we're going to return a string. And what do? We compute e left string. We can do this because the fields of plus satisfy type stringer. We compute e right string, and then we take those strings and splice them into the string, open parenthesis, first string plus second string, close parenthesis. And then we can use all that by saying, now we finally tie the knot. We're going to say, okay, what are all the things I want to do with an expr? I can eval it and I can string it. And now I can build e as an expr, which is plus of expr. So that means we'll be able to both eval and string these things of num1 and num2. And if I eval that, I get 3. And if I string that, I get the string 1 plus 2 in parentheses. So, very simple solution to the expression problem. Falls out immediately from Featherweight Go, as long as we've got this property, which I first showed you here, that the bounds, when you declare the receiver struct, could be bigger than the bounds when you declare the receiver of a method. So here, Ike implements any. Here, evaler implements any, and so we can write eval. Oops. And here, stringer implements any, so we can write string. And that's it. I was going to say more about monomorphization, but I'm out of time, so I won't. That's fine. You can look at the paper if you want. And I was going to show you a bit about how we formalize this, but I won't. But I'll just show you that for Featherweight Go, it's a pleasingly simple set of type rules and an even simpler set of reduction rules. And for generic Go, the syntax is a bit more complicated because now we put in all these type parameters. The rules are a little bit more complicated, but not impossibly so. And the reduction rules are still pretty simple. For future work, so Featherweight Go, as I said, is very simple. You might want to add more features, like arrays can be very interesting. There are some bugs in Java connected to arrays that we didn't catch because arrays weren't in Featherweight Java. So you might want something with other interesting features, like arrays. And then the most interesting thing in Go, of course, is that it uses channels for message passing. So we thought Cruiserweight Go, we would look at how do you add message passing features to model what's in Go. Somebody asked early on, I saw it in Slido, is this actually likely to become part of official Go? Well, we're working with the Go team. We have had an important impact so far. If you look at the first proposals they put forward, they involve something called contracts. Contracts were very nice syntactically, but it was completely murky as to what their semantics were. But in fact, all you need for bounds are not contracts, but interfaces. Interfaces are already in Go. They're already very well understood. So it's, excuse me. So the big impact we had is we went to them and we said, you know, you shouldn't use contracts, you should use interfaces. And we had long discussions with them. We tend to meet with the team about once a month. And I was meeting with them once a week once we wrote the paper to take them through the formalism in the paper so they could read all the Greek type rules. And they were willing to take the time to do that. And here's feedback from one of our members of the Go team who's a co-author. I want to thank you and your team for all the type theory work on Go so far. It really helped clarify our understanding to a massive degree, so thanks. So is this going to have some impact on Go? Yes, I think it's quite likely to have an impact. They're being very good, and even though we're pointy-headed academics, they're being patient and talking to us, and we're talking to them. And I think it's a very productive process. So I'll stop there. Here's a link to our draft paper on archive. And so if you want more details, you can go there. And I think I've gone a wee bit over. My apologies for that. I'd hoped to finish under time, but I'm clearly still getting used to this new remote world. So I apologize for being a bit over time and claim the pressures of technology as an excuse. Thank you very much.
Okay, thank you, Phil. That was very interesting. So I hope you have time to answer some questions on the Slido.
I'm happy to stay for a bit longer and answer some questions if people are happy to stay for a bit longer. Again, my apologies for going over.
No problem. So go ahead with the questions.
Clarification question. Are type variables shared across method? What is the scope of type variables? Nope, the scope of a type variable, I'll just go back and show you. So when we say something like this, what are the scope of this A and B? Just this declaration, nothing else. So I could consistently pick any other name. So this could be type Fred, implements eq of Fred, type George, implements eq of George, and then that is a pair of Fred and George, and so on. And the scope of a type variable in a method declaration, if it's the receiver, it's the rest of the thing, including the type signature here. If you have, another example, if you've got a type parameter in the method declaration, its scope is the rest of the type signature and the body. So anything declared here could also be used here. Anything declared here can also be used here, and both of these can be used anywhere in the body. Okay, I hope that clarifies the question about scope. So scopes for everything is very local. The scope for a method name or a type name is global, but the scopes for any kind of parameter, either a type parameter or a ordinary parameter, is local. Next question. Simon, what are the runtime consequences of the flexibility you offer? E.g., runtime lookup in dictionaries and so on. So if you monomorphize, it's no more expensive than Go as it is now. If we did something else, like passing runtime type representations, then of course you would have the cost of passing the runtime representations. So the trade-offs are about what you'd expect. It'd be very good to have detailed information, but things are still too early to have this. I should mention that the Go team is now doing a prototype. I should also mention that we have our own prototype, which actually shows you how these things execute. I'll run the prototype if somebody wants to see it running, but I won't bother otherwise. We have decided not to distribute our prototype freely because the Go team will be distributing their prototype freely, and we don't want people to confuse the two. But if anybody wants to look at our prototype, which is available now, just send us an email and we'd be happy to send it to you. Okay, new question from Adam. This cast and panic business makes me wonder, does Go require runtime type information? No, what Go has at runtime, as I mentioned, is an interface is implemented by a pair of things, a pointer to the struct and a pointer to the dictionary of methods over that struct. So that dictionary gives you all the information you need at runtime. So it's not quite runtime type information, it's just a runtime dictionary showing you where those methods are implemented, where to go to find the implementations of those methods on that struct type. Ilya, it's nice to get questions from familiar names, if not familiar faces. I wish Slido had a way of people putting in their photos as well, so you'd also get familiar faces. Ilya, is there subtyping in Featherweight Go? If so, how does the generic function signature capture the contravariance of the parameter type? Note, as I mentioned, things always have to, if you're matching a interface, the signatures must match exactly. The only thing that's anything like covariance or contravariance is this feature I mentioned where, like here, you can have your receiver with bounds more specific than the bounds in the actual declaration for the receiver. So that's a sort of covariance, not contravariance in the receiver. The only thing that you have for arguments is, as I mentioned, what you can pass as an argument is any type that implements this type. This is a struct type. So the only thing that's going to implement it is another struct type. But if this was an interface type, anything that implements that would be fine. The result here, again, the body can have any type that implements that. So if this was a list, for instance, right, we saw this here. the result type is list of B, and nil of B is a struct that implements list of B, in fact, again, by this very declaration. So that's okay. A cons here implements list of B, so that's okay. So there's no subtyping. There is implements, which is very similar to subtyping, and there are just certain places where an implements type can be used, where you can use any type that implements the type you want. So examples of that are passing arguments to a function, getting a result of a declared type. Anything that implements that type is fine. But when you're matching up against a method declared in an interface, or you're matching a method signature declared in the method declaration, they must match exactly on the signature. There's no covariance or contravariance. Oh, I wish I could see people nod. Somebody needs to do Zoom with nods built in. And the next highest question is from Anonymous. Can you explain in what ways Haskell subtyping is structural? I don't think it has subtyping, and the language seems heavily nominal. I'm not going to argue with you there. If you want to say everything in Haskell is nominal, I think that's a reasonable thing to say. There's very little subtyping in Haskell. There's no subtyping. The closest we get is subclassing, and the subclassing definitely is nominal. So that bit where I wrote structural in the slide for Haskell, maybe I should have written nominal. Maybe that would be more accurate. Mitch Wand, where does Kokke fit in the structural nominal spectrum? What about other systems, Agda, etc.? I should know the answer to that. I tend to think, so I'm most familiar with Agda, but I've also used Kokke. And I think structural is probably a better fit there. But if somebody wants to leap in the chat where Kun can see it or somewhere and say, nope, you've got that wrong, Phil, and Kokke and Agda are much more nominal, I would stand to be corrected. But I think they're more towards the structural. But again, they don't have any form of subtyping at all. Right? The closest to that is implication in propositions, which you actually need to prove. So there's nothing very much like subtyping going on there. Next question from somebody who I've not met before. Hello, Bjorn. Does this solution to the expression problem lead to issues similar to Haskell's orphan instances? I don't know. Can somebody tell me what an orphan instance is? I've not heard that term. So Bjorn, I think I may not be able to answer your question in real time, but if you send me an email where you explain what an orphan instance is, I'll try to answer it offline for you. I'll move on to the next question from Jesper. Oh, let's see. Why did I stop sharing so you can see my face? Hello. And from Jesper, a non-technical question. Which do you enjoy more? Work on industrial languages like Java or Go, or working on academic languages like Haskell or Agda? So the answer to your question, Jesper, is it's a bit like eating. You will know that most people are equipped with an ordinary tummy and a separate dessert tummy that you can put ice cream in even when your ordinary tummy is full. So they're sort of orthogonal. So I really enjoy doing technical work on things like Haskell and Agda. And I also enjoy working on things like Java and Go, where there's strong constraints imposed on you by what's already there. And so it's a very different sort of work, but it can be very satisfying. And if people ask me, which should I do, theoretical blue sky work or deeply practical work that's constrained by legacy stuff that's out there that you want to work with, my answer is do a bit of each. I think they're both rewarding.
So Phil?
Yeah.
We have time for one more question and then we should wrap up.
Okay. You've been looking at the questions more than me, so why don't you read out a question to me and I'll answer that one.
Oh, just take that one that's highest up.
Okay. Do you have access to higher-kinded polymorphism in Featherweight Go? No, we have not looked at all at higher-kinded polymorphism in Featherweight Go yet, nor does generic Java have higher-kinded polymorphism. So we're not looking at that at all yet. Sometimes there's an advantage to keeping things simple as you get started. Okay, I guess I'll stop there. Thank you very much to everybody for attending. I'm sorry we couldn't interact in the usual way. I hope this was somewhat satisfactory. I think we're all going to be developing skills for doing this. It's great that we can attend seminars around the world, and I look forward to us learning how to, I look forward to learning how to do this better. I look forward to the community learning how to do this better. Thank you again for your attention.
I think you did an excellent job, Phil, and I thought it was very nice to hear about this. So I would like to thank the speaker. And then I welcome all of you back next week when Robbie Findler will talk. So see you next week. Thanks all. Thanks, Phil.
Okay. Thank you all for attending, and thanks to Koen, John, and Mary for inviting me.
Unknown caller.